Okay, valence bond theory. The Lewis model is an oversimplification. It works for a lot of things, but there are some things like resonance that it just can't handle. And so more advanced bonding theories that use quantum mechanics help us to understand some of those missing pieces. These are quantitative approaches. They use a lot of math, and they predict bond angles, bond length, bond strength, all kinds of stuff. Dipole moments, you can calculate what the dipole moment is. We are not going to look at the quantitative aspect of these models. We're going to look at them qualitatively, okay? Because the math is too much and it's not necessary for us. So valence bond theory, and just a cautionary word here. So I'm going to go through this stuff and it's going to seem very, very confusing. And then I'm going to relate this to the hotel, and we'll have some pictures and stuff, and hopefully it'll start to become clearer there. So try to stay with me, even if it doesn't seem to make sense. Ask questions. It really is a cool bonding model. It really is. So we've learned that electrons reside in quantum mechanical orbitals. Those are localized on individual atoms. We talked about S, P, D, and F orbitals. Remember, the S is spherical, and the P's are like two balloons, and then the D's and the F's get really weird, and there are all these like weird shapes around the nucleus. And those are essentially standing waves occupied by the electrons. Well, in valence bond theory, we recognize that we can combine atomic orbitals together to make a new kind of orbital called a hybrid orbital. So we can take like an S orbital and a P orbital and combine them together. Those are called hybridized orbitals. When two atoms approach each other, the electrons of each atom are repelled by each other and the nuclei are repelled, but the electrons of one atom are attracted to the nucleus of the other atom. So there's complicated interactions here. And valence bond theory is looking at the energy changes that result from the interactions of the electrons and the nuclei. A chemical bond will form if those interactions result in a lower energy. Everything's trying to go to a lower energy. So this is a graph, energy going up on the y-axis, and distance between two hydrogen atoms increasing over to the right. In the middle here, we have zero energy. And you could think of this a little bit like being the potential energy of a rock, where this is sea level. And if the rock is right here in the shallow end of the lake, and you come and there's a drop off, the rock is going to roll down. Maybe make it a boulder, because the rock might not be round enough to roll. A boulder is going to roll down to the bottom, right? It's below zero altitude. That's okay, it's still going to go down, right? So this is zero energy, and going down, becoming more negative, that's lower, right? So here we have two hydrogen atoms. As they begin to approach each other, there's some attraction, and that lowers their energy. And they get closer together, and there's more attraction. Their orbitals begin to start overlapping. And it lowers, and then they get to this point, and we reach the minimum. And so there is a maximum attraction giving these a minimum energy. If we keep getting them closer together, now they start to get a little uncomfortable. So if you think of two people, you're a nice, attractive person, this other's a nice, attractive person, and you meet each other, and you're like, oh, and you come together, and you start talking to each other, right? And you get to this kind of a sweet spot of where you're talking, but then if that person turns out to be one of those close talkers that stands too close to you, right? Then you're like backing up, because it's not right. You don't feel comfortable. So there's this ideal distance between the two atoms where the attraction of electrons to nuclei is maximized and the repulsion of nuclei is minimized. You get closer together and the potential energy goes way up. And so this is going to be the bond energy over here. and the distance between them is the bond length for the hydrogen-hydrogen bond. Any questions?
So this is like an equilibrium point, where it's minimizing energy and also minimizing the motion.
It is a little bit, it's not a fixed thing.
Okay.
It's not technically an equilibrium, but are these two atoms always this distance apart? No. There's actually some vibration in that bond, and so it could move a little to the side as it comes apart and goes together, but it's going to stay, and the average will be right here at the lowest point.
Okay, so this is all still like very statistical.
Yes, this is very statistical. Just to give us the idea of there's attraction, but then we get too close and there's repulsion. So there's a sweet spot where you minimize repulsion and maximize attraction. And that's where we get the lowest energy, and that we measure that's the bond length. So that interaction energy is usually negative, below zero, is stabilizing, when the interacting atomic orbitals have two electrons that can spin pair. So electrons are repelled by other electrons, right? Because they're both negative charges. And yet we've seen in orbitals that two electrons can be in an orbital and be okay with each other because of spin pairing. One will be spin up and one spin down, and then they're okay in the same orbital. So our attraction here will be negative, meaning it will be attractive when the orbitals that are overlapping have a total of two electrons, and those electrons will spin pair. Normally, each electron brings one electron, and they pair up, and they're good. You can also have sort of a charity case where one atom has an orbital with two electrons in it, already spin paired, and the other atom has an empty orbital. And it's like, well, I'm feeling sorry for you because you don't have any lunch, and so I'm going to share my lunch with you, right? Instead of this person bringing the sandwiches and you bringing the fruit and you sharing together like that, it's one person doing all the sharing. That's called a coordinate covalent bond, and those are important, but we're not going to talk much about them. So the idea here for valence bond theory, we're talking about chemical bonds being overlap of orbitals. So when we have half-filled orbitals approaching each other, the orbitals can overlap with each other, the electrons can spin pair, and then that forms the chemical bond. So this is a summary of what we've talked about. Valence electrons in a molecule are in quantum mechanical orbitals. Chemical bond is from the overlap of two half-filled orbitals with spin pairing of the valence electrons. And then the geometry of those overlapping orbitals is what determines the shape of the molecule. Any questions yet? Maybe it doesn't sound too bad, but you're not exactly sure. So let's look at how this might work out. So here we're going to look at H2S and see how this model would work. So here's sulfur, and again, we're only looking at valence electrons. So here's the orbital diagram for the valence electrons of sulfur. All right, so this should be familiar. Sulfur has two half-filled orbitals. And then we have two hydrogen atoms. Each hydrogen atom has a half-filled orbital. And so what we can predict is that this half-filled orbital will overlap with this half-filled orbital and make a bond. And that's a hydrogen-sulfur bond. And this other orbital would overlap with the other hydrogen and make a bond. So over here, this funny balloon shape here is the sulfur atom. So the blue in the middle is the s orbital, and we see the two arrows there. That's this one right here. Bless you. And then there's an orbital going up and down, and then there's two that are perpendicular to that, and those are these p orbitals. This one is full. It's got a pair of electrons. The other two are half-filled. So this orbital is half-filled, and that's going to overlap with the half-filled orbital of this hydrogen. Those electrons spin pair, and that's the bond. This third orbital of sulfur, third p orbital, has one electron, and the hydrogen has one electron, and their orbitals can overlap and form a bond. Does that make sense? Yes?
Does it make a difference that these, like, the hydrogen and the two half-filled boxes for sulfur, they're both have spins, they're both positive?
That's a good question.
One flip or...
So we show all of these half-filled orbitals with a positive spin just by convention. They can flip their spins. Yeah. So what will happen, even though we've drawn these, this is up arrow and this is up arrow, one of them will flip so that they can spin, pair, and be okay. Otherwise, they won't be happy. Any other questions? So this would predict that the bond angle here, this is a bond and this is a bond. It would predict that that bond angle is 90 degrees. Because that's the orientation of those p orbitals. But when we look at the actual bond angle, it's 92 degrees, and Vesper theory predicts something less than 109.5. So this overlap business needs some help. It's not quite making it yet. Let's look at carbon and hydrogen. So here's carbon. Carbon has two half-filled orbitals, and hydrogen again has a half-filled orbital. And I'm going to put another one in here. So here's the full orbital. The s orbital is blue, and the p orbitals are red. So this orbital has one electron from the carbon, and it's overlapping with this hydrogen orbital, right? So we've got these two overlapping to make a bond. And then we have another p orbital that's half-filled, and that's going to interact with the other hydrogen atom, and they're going to overlap and form a bond. You okay with that? So this idea predicts that we would have 90-degree angles between these bonds, and that the formula would be CH2, because there aren't any more half-filled orbitals for carbon to bond with anything, right? So just doing it this way, we say, well, it's CH2 and the bond angle is 90 degrees. And then we're wrong, because it's actually CH4 and it's a tetrahedron. So again, something's missing here. And I forgot to stop the video, so these are just going to be two sections mashed together. Oh, wow. So far, we've been operating on the idea that in a molecule, the orbitals are the same as they are when an atom's all by itself. Well, that's not actually true. When the atoms come together to form a molecule, their orbitals change. So we talk about hybridizing the orbitals. Hybridizing, remember, the orbitals have an equation that describes them. They are a standing wave that can be described mathematically. And so you can take those mathematical equations and you can combine them together. It's not as simple as averaging, but it's the same idea, right? You take all these things together and then you divide it up. So we hybridize these orbitals, and then the result is called hybrid orbitals. So we have standard atomic orbitals, that's what we learned about previously, and then those orbitals can hybridize. This corresponds more closely to the actual distribution of electrons in molecules and fixes the problem that we saw in the last two examples. So these orbitals are still localized on individual atoms, but their shapes are going to be different and their energies are going to be a little different than the standard atomic orbitals. The hybrid orbitals minimize the energy of the molecule by maximizing the overlap. So if you've got a p orbital and an s orbital and you're trying to overlap them, you'll get a certain amount of overlap. But if you hybridize the orbitals, you can get more overlap. And we'll look at what they look like in a minute. So it's going to do this because it results in a lower energy. The hybrid orbitals, sometimes I just can't resist. So a regular p orbital looks something like that. That's one orbital. And so if you're overlapping with another atom, you can only overlap part of one lobe. And the rest of this is not overlapping at all. When we hybridize orbitals, we're going to get something that looks more like this, where one lobe is larger and the other lobe is much smaller. Now this lobe overlapping with another atom will have more overlap than a regular unhybridized p orbital. It does require energy to make these hybrid orbitals. So they're not just going to happen willy-nilly. They will only happen if there's a payback in energy. It's a bit like an investment. You make an investment in the business, and then you're only going to do that if you're going to get a return on the investment. You don't put money in just because you like throwing money away. You put money in because the hope is that in the future, the business will grow and your profits will grow and you'll get all that money back plus some, right? So there's energy needed to hybridize, but then when the bonds form, more energy is released and there's a payback, so a lowering in energy. We're going to focus on hybridization of the interior atoms, and we're going to assume that the terminal atoms, the ones along the outside, are unhybridized. That's not true, but it's good enough, right? And it is true that atoms that have more bonds are more likely to hybridize. A terminal atom generally has one bond, so it will hybridize, but not as much as, say, a central atom that has 4 bonds. That's going to hybridize more extensively. So that's why we can ignore those. This first statement I kind of think of as conservation of orbitals. The number of standard orbitals added together always equals the number of hybrid orbitals. So if you take 3 regular orbitals and you hybridize them, you're going to end up with 3 hybrid orbitals. If you start with 2 orbitals, you'll end up with 2. You can't take 2 orbitals and hybridize them and make them into 5 orbitals. It's always the same number. The particular combinations of the orbitals that you're hybridizing is going to determine the shapes and the energies of the hybrids. And then one of the things this really bothered the class yesterday, and it should, how do you know which hybridization to use? Well, the particular type that occurs is the one that yields the lowest energy, and that would require all kinds of calculations and stuff, and we're not going to do that. So what we're going to do is we're going to use Vesper theory, electron geometries, to predict what the hybridization is. And that's good enough for our purposes. Okay, how this would work. The first one we're going to look at is we're going to take an s orbital and the 3 p orbitals in the second level, and we're going to hybridize them. So we've seen energy diagrams or orbital diagrams like this before, where we've got the energy is higher as we go up, and here's the 2s sublevel. It's got 1 orbital, and the 2p sublevel has 3 orbitals, and these are higher in energy, right? And so we learned that the s orbital will fill, and then the p orbitals will start to fill, and they'll fill with parallel spins until they have to pair up. Remember that? I also had the analogy of the hotel, and so this was like the S room on the second floor, and this is the P room on the second floor. And so There's the S room. And here's the P room. And of course, there isn't like a hallway or something between those two rooms. We draw a gap there so that we can see that they're separate rooms. But this is a wall, basically, right? That's a wall. So here's the S room, and here's the P room. And there's 3 beds in the P room, and there's 1 bed in the S room. The hybridization is like remodeling the hotel. So what we're going to do here is we're going to take these 2 rooms and make them into 1 room. So we're going to knock down this wall. And now we have 1 big room with 4 beds in it. We just removed the wall. Does that make sense? So this isn't an S room or a P room anymore. And so we're going to call it SP3. SP3. Because we took the S and 3 P orbitals and we combined them together. So we're taking all 3 of these and we're hybridizing them, averaging them in a complicated way. And we end up with 4 orbitals that have the same energy. Because in this room, now we have 4 beds. You can't charge more for that bed than this other bed, right? Because the hotel manager doesn't know which bed you're sleeping in. It's you get to stay in the room. It's just whichever bed you choose, right? So the price here is sort of an average of the prices of the 2 hotel rooms. So the S room was cheaper and the P room's more expensive. And so when you average that, the energy or the cost is going to be in between. It's higher than the S orbital, but lower than the P orbitals. That makes sense? Each of these will have their own bed. Yeah, so these orbitals are the beds, and they can each hold 2 electrons. And so what we're doing is we're taking these orbitals that were different in energy, and we're combining them together so they all have the same energy. So that energy is going to be between the high and the low that they were before. So the P orbitals were up here, the S orbital was down here. When we hybridize them together, we make them all the same energy. That's called degenerate. They're all the same energy. They're all going to have the same shape, but the shape's going to be distributed around like the P orbitals were, distributed equally in 3-dimensional space. Yes?
So the same rules apply
Yes, so Hund's rule still applies. So this is carbon that we're looking at, standard atomic orbitals for carbon, and there'd be 2 electrons in the 2s orbital, and then in the 2p subshell, each of these orbitals would have 1 electron. So we have 4 valence electrons. So imagine those electrons went out for lunch, and while they were gone, their room got remodeled, right? The wall got taken down, very, very fast construction. They come back, and now there's 1 room with 4 beds. So they're like, well, cool, we're each going to take our own bed, right? There's no reason for these 2 guys to pair up like they were before. And you see how this gives us 4 half-filled orbitals now, when before we only had 2. Any other questions?
So like the energy it'll be somewhere between.
Right. It'll be lower than the P's, but higher than the S. Yeah. So if you think about it, it's like, well, if you took these 3, I'm getting all these reminders of payments that are going out to this school, and it's not every lunch charge separately coming through. It's not supposed to do that when I'm in presentation mode, but it's doing it, and it's really distracting. Sorry about that. If you think about these 4 people, 2 of them were staying in the P room and 2 were staying in the S room. These guys were paying less, these guys were paying more. But if you average what they were paying, it would be this amount. And so now they're all paying the same, but they're each getting their own bed, right? They're each getting their own orbital. Does that make sense? Now, does it cost energy to do that? To remove a wall, it costs some money, right? So somebody's having to do some investment here to remove that wall. So what would this look like? Oh, I'm glad you asked. Here's an s orbital, and here's the px orbital, and the py orbital, and the pz orbital. We're going to take these three orbitals, they're like standing waves, they're wave functions, right? And we're going to combine them and make 4 new orbitals. And the easiest thing here is just to say, okay, I'm not sure exactly how that works out, but okay. The s orbital is spherical, right? And each of these is symmetrical about the nucleus. And what happens when we combine these together is we get non-symmetrical orbitals. So one lobe gets bigger and one lobe is smaller as a result of all of this. There's 4 of them, and they're going to spread out equally in 3-dimensional space. That's what the p orbitals did. That was as far away as they could get by being along the x, y, and z axis with 90-degree angles. Now we've got 4 of them, and those are going to point towards the corners of a tetrahedron to spread out. So each of these orbitals does have 2 lobes, but one of them is very small. And when we try to draw all 4 of them together, it gets really confusing if we try to show all those little lobes. So we ignore that little lobe. It's there, but it's not involved in the overlap, and so we just don't draw it. Okay? So one of the things that was confusing yesterday is we are used to looking at a p orbital and seeing 2 lobes, like 2 balloons, and saying that's one orbital, right? But then over here, when I show you this, there's 4 balloons, and you're like, well, that must be 2 orbitals then, right? Because these guys have 2 balloons, 2 lobes. Each of these is the big lobe of an orbital, and there is a second lobe, but it's puny, and so we're not drawing it. So 1 orbital, 2, 3, 4. Okay?
Is it just that you're not drawing the little lobe in those orbitals, or do they exist and they're extending into the big lobe of another?
That's a good question. Am I just not drawing them, or do they just kind of mash into other ones? Because of the angles here, like the lobe for this one would be over here. It would not be directly into the other. And so this one would be behind, and this one would be down, and yeah, it gets ugly real fast.
But they're so small that
They're so small that they don't really matter, yeah. And, you know, it is disturbing, but orbitals can overlap with each other because they're standing waves, right? We have that wave-particle duality, and the electron's a particle and it's a wave at the same time. And here we're looking at the particle as a wave, okay? So if we look at the hybridized orbitals for carbon and draw an orbital diagram, we're going to show 4 boxes all together. This is like one of the hotel rooms with 4 beds, and it's called sp3. I originally had 4 beds. I still have 4 beds. No beds were created or destroyed in this remodeling, right? I started with 4 orbitals. I still have 4 orbitals. That's really important. You have to have the same number that you started with. When we put the electrons in there, like we mentioned earlier, we do Hund's rule. So if I'm putting 4 electrons in here, they're each going to take their own orbital before they start pairing up. Now if we look at how this would overlap with hydrogen, so there's a hydrogen, here's a hydrogen, here's a hydrogen, here's a hydrogen. This half-filled orbital of carbon can overlap with a half-filled orbital from a hydrogen. And these two can overlap, and these two can overlap, and these two can overlap. And now we're saying, well, this looks like it's going to be CH4, right? Because carbon has 4 half-filled orbitals now. And that matches up with observation. CH4 is the smallest molecule composed of carbon and hydrogen. Then when we look at electron geometries or molecular shape, these hybrid orbitals, and notice what they did here. They use blue for s orbitals, and they use red for p orbitals. And when you mix blue and red, what do you get? Purple. So these are mixed, right? This is a hybrid. I like that. So these are our 4 hybrid orbitals. They make a tetrahedron. And then when they overlap with the hydrogens, that's where the bond goes. It goes out to form a tetrahedron. This matches up with VSEPR theory and with observation. Hybrid orbitals. Any questions? One of the things I like about this theory is, at least when you have somebody else drawing the pictures for you, it's more visual. Yes? Yes. So the 1s orbital has 2 electrons in it for carbon, but those are core electrons, and we do completely ignore those.
So we only use the higher.
Yes. We only use the top floor of the hotel, the valence electrons. The valence electrons, on average, extend farther away from the nucleus, and so those are the ones that are going to interact with other atoms. Yep, excellent. Anybody else?
So the hybridization, does it only work for elements that don't have full
That's a good question. Does it only work for elements that don't have full valence shells?
Yeah.
Right. So what are the elements that have full valence shells? The noble gases, right? And the noble gases do not form a lot of compounds. When we look at helium and neon, valence bond theory predicts that they're not going to form compounds, and helium doesn't. I think neon might make one, but I'm not sure about that. When we get into the bigger ones, the third period, like argon, krypton, xenon, in the 3rd, 4th, 5th levels, we have d orbitals. And so what we'll find is that you can expand into that d room on the hallway, even if it's empty, right? But helium and neon, 1st and 2nd level, there's no empty room to expand into. So we won't see anything with them with hybrid orbitals. What if we have a lone pair? Well, that works out also. So here we could have nitrogen, and if we draw the hybrid orbital diagram for nitrogen, sp3, how many valence electrons does nitrogen have? 5. So we'll stick those in here. I've given up on changing to red for the electrons. It's too hard. 1, 2, 3, 4, and then the 5th one has to pair up. And here we're looking at ammonia, so we're going to have hydrogens. So here's a hydrogen, and here's another hydrogen, and here's another hydrogen. So we could have these two overlap, right? And we could have these two overlap, and we could have those two overlap. That makes sense? This one is already full, so that one's just going to sit there. That's our lone pair. So we hybridize the s and the 3p orbitals to make 4 equivalent orbitals. One of them has a pair of electrons in it. The other 3 are half-filled. The half-filled orbitals can overlap with the half-filled orbital of hydrogen to form a bond. And then we would predict that the geometry here would be tetrahedral for the electrons, and that the shape of the molecule would be trigonal pyramid. We observe that the angle here is less than perfect, less than 109.5. And in Vesper theory, we explain that as saying that the lone pair is more repulsive. Valence bond theory explains that because the hybridization of those orbitals is less complete due to the lone pair. So we're talking about these as if they hybridized completely. That's easiest to think about. They actually don't have to hybridize completely, and so they can be a little unsymmetrical, and that's why the bond angles are wonky. We don't have to worry about it though, but it does bother some people. Any questions? There are lots of different combinations of orbitals that you can hybridize. We looked at sp3. Here we're going to look at sp2, the s orbital and two p orbitals. We're going to combine these. And so in the hotel, we'll draw it down here. This was the s room and this is the p room. Those are the walls, not to be confused with the individual beds. Maybe do it this way. Okay. Here, we're going to remodel the room, but we're not going to put all of it together. We're not just going to knock down the wall. We're going to knock down the wall and we're going to build it in a different place. So we're going to take out this wall and we're going to put it over here. So over here I have a regular p orbital, and then these guys I'm going to call sp2. And we're not going to go into why would they want to do that. We don't need to think about that. So an s orbital and two p orbitals. Those hybridize, make three degenerate equivalent orbitals that are in between the energies of the original ones. And then what about this guy? He's just sitting there, not changed. Okay? Any questions? What does an sp2 hybrid look like? Well, here we're taking an s orbital and two p orbitals. It doesn't matter which p orbitals you take. We're just taking the ones that happen to be in the plane of the screen because it's easier to draw. You hybridize these and you're going to get a similar shape. It kind of looks like a drumstick, right? It's big and fat on one end and kind of skinny on the other end, smaller on the other end. Yeah. So we're going to make three of these drumstick orbitals, and they're going to spread out equally in space. Well, because there's three of them, they're going to be planar, and they're going to spread out at 120 degree angles. And again, in this drawing, we're not seeing the little other lobe. Okay, so the other lobes are there, but they don't participate. They're not involved in the overlap to bond, and it's difficult to draw them, and so we don't. But that's where they would be. Any questions? So if we look at H2CO, which is a molecule we drew the Lewis structure of before, and we found that it looked like this. At this point, I'm just telling you this molecule has sp2 hybridization. I'll explain how you would figure that out later, but for now I'm just saying it has sp2 hybridization. So here's the unhybridized carbon atom, and we're going to hybridize its orbitals. So we're going to take the s and two of the p orbitals and put them together to make sp2 orbitals. And this one that was left out just stays there. Now let's go back to this one for just a minute. And my pointer, no, it's not going to work. So these hybrid orbitals are between the s and the p orbitals in energy. They're relatively close to the p orbitals. There's an energy difference there, but it's not as big as between the s and the p, right? So here, carbon has 4 valence electrons, and they come back to this new arrangement of their rooms. And the first 3 electrons go in here, and then the 4th electron, we would expect that it would pair up here because this is lower in energy. The difference here now is very small. Maybe it's $5 a night for the extra room. $5 a night to have your own bed and your own space. It's probably worth doing, right? So those 4 electrons can spread out and occupy all 4 of those because the energy difference between these is smaller now, okay? Because that's another thing people struggle with. Well, shouldn't this electron pair up over here? Now it's going to spread out because the energies are more similar. So here we have our original atomic orbitals. The carbon is going to hybridize and do this. Here we've got oxygen and hydrogen, and we need to put another hydrogen in here. Stick it over here. And I'm going to get that out of the way. So the carbon now has 4 half-filled orbitals that it can overlap with these other atoms. So we can get an overlap between the hydrogen and one of those orbitals, and an overlap between the carbon and one of those, the other hydrogen and one of those orbitals, and the oxygen and one of those orbitals. And then what we have left is this half-filled p orbital and a half-filled p orbital on the oxygen. And those can also overlap. Here we have 2 overlaps between the same 2 atoms, the oxygen and the carbon, and that's what gives us the double bond. We got a picture coming up, but any questions? Why doesn't it become an sp3? That's an excellent question at this point because I told you it didn't. We'll see in a minute. Isn't that pretty? Glad I didn't have to draw that. So let's figure out what this is trying to show us. Here's the oxygen. The oxygen had sp2 hybrid orbitals. These are the purple balloons. I'm sorry, carbon. Yes, thank you. Please correct me, I need it. Here's the carbon with the sp2 hybrid orbitals, right? They're going to spread out in space and make a triangle. And then there was one p orbital that was left unchanged, right? So there's a p orbital. Okay? Here's our hydrogen, has a half-filled s orbital, can overlap and make a bond here. Our other hydrogen can overlap with this orbital. And here's our oxygen. Now, in the oxygen, to make this as simple as possible, we're not showing the p orbital that has a lone pair in it, a pair of electrons, and we're not showing the s orbital from its electron diagram. We're only showing the 2 that were half full. So, if you look at the oxygen there, we have 2 half-filled p orbitals. We're assuming that the oxygen doesn't hybridize, and so in this diagram, we're just looking at those. So we've got a p orbital, oh my goodness, It's not supposed to be that wobbly. There's one p orbital, and here's another p orbital from the oxygen. So one of these p orbitals will overlap with the sp2 hybrid orbital from carbon and make a bond. This one is perpendicular to that one. It's at right angles, and they can't bend around. So how can this one overlap with anything over here? It can overlap with an unhybridized p orbital, and it does that through a side-to-side overlap. This is end-to-end. End-to-end is a much better overlap. It works out better. It's lower in energy. It's a stronger bond. This is a side-to-side overlap. Not as great, but it still happens. If the carbon here was sp3 hybridized, it would not have this p orbital that could overlap side by side with this p orbital. And we can't have, well, say that again. I don't think I quite understood.
So instead of having that sp orbital that combines with the p orbital of oxygen,
Mhm.
why doesn't it just have another p orbital to combine with both of those two groups of oxygen?
So that's a good question. Why don't we have maybe sp hybrid here and an unhybridized p orbital? Because I really don't know how to answer that. I really don't. Because the mathematicians tell us it doesn't do that. This is lower in energy than that. And yeah, so some of this stuff, there definitely is a definite answer for, but we can't necessarily get to that answer this morning.
The lower the energy and where it's
Yeah, it's going to hybridize and overlap in whichever configuration results in the lowest energy, the best overlap. And so I can't explain mathematically why that is. I will give you a rule of thumb. It's actually on, you do it on your fingers, of how to decide what hybridization I should use. It's going to match up with the Vesper theory, and we're just going to be okay with it. But that's a good question. Yes?
So this lone p orbital on this C, that's, if you go back to the other
This
side,
one?
Yeah, if you go back to the previous slide, it's that lone.
Yeah,
there.
it's this one. I can't draw on here without messing up the other one. But that p orbital is the red one.
So
Yeah.
in a sense, like, you choose this hybridization to leave that p orbital in
Mhm.
order to form that double bond with
Right.
oxygen.
Yeah. So what we'll find is when we form a double bond or a triple bond, we always have an end-to-end overlap first, and then we have unhybridized p orbitals making up the second and the third bond. These are different kinds of bonds because they're different sorts of overlap. So this is end-to-end. Those are called sigma bonds. And this side-to-side overlap is called a pi bond. So pi bonds happen between p orbitals. Sigma bonds happen between s or p or hybrid orbitals. It could be anything. If we look at the letter sigma, well, it's not very good, sigma, is like an O with a little tail at the top, right? And this circle here, if you stood at the oxygen nucleus and looked down this bond length, you would see a sphere, right? You're looking down like a tube, right? And you just see it being round. That end-to-end overlap gives us a round orbital. A round bond. It's symmetrical. And this is going to be very different, right? And so that's a pi bond. And if it helps you at all, if you tip your head sideways, kind of looks like a pie, right? I don't think they did that on purpose, but I noticed it and I like it. So there it is. So sigma bonds and pi bonds. So let's talk a little bit more about those. So the pi bond happens when you have p orbitals and they are side to side. So they're parallel with each other in space and they're going to overlap side to side. Now this kind of looks like it's two bonds, doesn't it? Because there's this piece on top and the piece on the bottom. But it's like this is one orbital, it's one bond, it's just got a piece at the top and a piece at the bottom, and it can do that because it's a standing wave, and the electron does not have to go through space to get from one side to the other because it's a wave too. So it's, we're okay with it. These two p orbitals can overlap end to end, and that would form a sigma bond. You can only have one sigma bond with p orbitals because the rest of these then are going to be perpendicular, and that's not going to work, right? I can't have these end to end and these end to end. So this is a sigma bond, that's a pi bond. Sigma bond gives us better overlap, it's lower in energy, so that's always going to happen first. And the pi bond would happen next because it still lowers the energy, but it's not as much. So, important idea here, the electrons occupy both lobes. So I'm showing the pair of electrons here, but that pair of electrons is actually occupying all of this. Any questions? So we can label these bonds, and we're going to do this on the worksheet. We're going to identify the bonds, and we do that by specifying which type of the bond it is. Is it sigma or pi? What are the two atoms that it's between, and what are the orbitals involved? So for this one, here in the middle, that's an end-to-end overlap, so that's sigma, colon, this is between carbon and oxygen, don't really care which one you put first, carbon and oxygen, and then in parentheses we say what orbital on the carbon is participating in. Well, that's the sp2 hybrid, so sp2, and on the oxygen, it's just a regular p orbital. Over here we have two bonds that are the same kind. So there's sigma, an end-to-end overlap. You're like, well, that doesn't look, how do you have an end of an s orbital? Well, it's overlapping the end of the sp2 orbital. So sigma bond between carbon and hydrogen, and we're using the sp2 hybrid orbital for carbon and the s orbital for hydrogen. And then up here, and this is part of the same bond, that's a pi bond between carbon and oxygen, and it's a p orbital on the carbon and a p orbital on the oxygen. All of our pi bonds will be p and p. There won't be hybrids in there. Any questions? So we get more insight using valence bond theory than we do with the Lewis model. In the Lewis model, the double bond is two pairs of electrons, and for all we can tell, they are equivalent, right? They're equal. But in valence bond theory, we see that one of those bonds, the sigma bond, is stronger than the pi bond. And we observe that experimentally, that when we break bonds, the one bond breaks first. You can break one of the bonds without breaking the other one. You break the pi bond first, and you can leave the sigma bond intact. Lewis theory doesn't really help us out much with that. When we look at a double bond in Lewis theory, Lewis model, anytime you see the double bond, it's always a sigma and a pi bond. So here, when we see this double bond right here, that double bond in the Lewis structure, it's a sigma bond and a pi bond. This also helps us to understand some aspects of the nature of these bonds. I kind of destroyed my things here doing other stuff yesterday. So here we're going to look at two similar molecules. Here are their Lewis structures. Here we have a carbon with a single bond to another carbon, and then on each carbon we have two hydrogens and a chlorine. And we could draw the valence bond diagram or illustration for that. The carbons here are going to be sp3 hybridized, and they're going to form a sigma bond with the other carbon, a sigma bond with the hydrogen, a sigma bond with the hydrogen, and a sigma bond with the chlorine. This sigma bond here is symmetrical, and there is free rotation around that single bond. So here I have a ball and stick model of this. So here are in the green are the chlorines, and I've got a single bond here. And this bond can rotate. It can spin around, and it does. So at any given time, you could have the chlorines on opposite sides of the molecule, or they could be on the same side of the molecule, or they could be anywhere in between. It spins.
You usually spend being constant, or it would be placed repeatedly.
Do I mean constant free spinning? Pretty much, yeah. I mean, it's not like a little helicopter or something, but it's just free to move around, and it's probably going to spin relative to forces that are acting on it from outside. Like if it comes to something that the chlorine's attracted to, the chlorines would probably swivel over to be closer to that, but it could be any place. Here we...
Yeah, but I didn't know if there was a polar between the two.
Not really, no. So over here, we have a double bond between the two carbons. So this is going to be an sp2 hybrid. We're not going to worry about Y just yet. So this is similar to the molecule we were just looking at in the previous example, where we have this pi bond and the sigma bond. This pi bond extends above and below the sigma bond. And so we make a model with the model kit, and the model kit is not exactly like that, but it kind of works. Here I have two bonds between these two atoms, and I can't spin them anymore. It's stuck, right? In order for one of these to rotate, I'd have to break the pi bond. It can't rotate. So this bond does not rotate. And there are actually two separate molecules. They're very, very similar, and yet they're not exactly the same, where you can have the two chlorines on the same side or the chlorines on opposite sides. And they can't go back and forth because of the double bond.
How does that change the properties of that bond?
How does it change the properties? Well, with the two chlorines on one side, the chlorines are more electronegative, and so this molecule would be more polar than if you have one on each side. Yeah.
So more polar, so then it's more reactive, it'll be more stuck with other molecules.
Yeah. Exactly how it's different and why that matters is something you investigate more in OChem. But yeah, this would react with other molecules to produce different things.
Okay.
Yeah.
Is it naturally one or the other, or is it just
That's a good question. Is it naturally one over the other? And so here we're looking at the same two molecules. This one with the single bond, we've got free rotation, and so it can be like that or anything in between. And here this is the one we were looking at on the previous slide with the double bond, and the two chlorines were on one side. And so it's always going to be like that. It can't swivel around. If we put the chlorine on the other side, it's a different molecule. Now, the question was, is it like 50-50? It depends on how it was made. There are some processes where you can make almost exclusively one or the other, and that's one of the puzzles that's fun to solve in synthetic organic chemistry is how can I make one of these isomers and not the other? And then how could I separate them if I have a mixture? And what is the mixture? And some of them you'll get a 60-40 mix, some of them will be 50-50, some of them you can make just one and not the other. Lots of possibilities there. Any other questions? The little prefix here, cis and trans, describes the relationship of these different atoms. So here the two chlorines are on the same side of the bond. So that's the cis side. Same side, like your sister. If you're on good terms with your sister, this works. If you and your sister, were attacked or something, you'd be fighting together, right? You'd be on the same side, not your sister fighting against you. Trans is when they're opposite, like the transatlantic, goes going across the Atlantic Ocean. Right? Trans means across. Okay, we're going to look at more combinations. This is if we took the s orbital and only one of the p orbitals. So like the previous one, we're essentially moving a wall over, but this time we're just moving it over one bed. And so we've got this hybrid where we've got two sp hybrid orbitals, and again, they are between the energy of the p and the s. And then these two that didn't hybridize are just sitting there unchanged. Okay? Here we're combining an S and a P, and in some ways it'd be easier if this was shown first, because I think it's easier to imagine how you can combine this s orbital and this p orbital and end up with those two things. That's a little easier to visualize than the s and three p's all together jumbling up. So we're going to combine these two things. We're combining two orbitals. We're going to get two orbitals. And one will have its major lobe off to the right, and the other will have its major lobe off to the left. I did that backwards. You get it. When we show these together, that looks a lot like a p orbital, doesn't it? This is two sp hybrid orbitals. We're not showing these little stunted lobes. And the big clue here is that this is purple. Okay, this is purple and that's red. So the purple in these illustrations are hybrid orbitals. Those are going to be in a linear geometry. The remaining unhybridized p orbitals would be at right angles, one up and down and one in and out of the plane of this screen. So let's look at acetylene. Let's draw the Lewis structure. There's a Lewis structure. It's very similar to that. Acetylene has sp hybrid orbitals for now because I told you so. So here's the carbon. Here are the atomic orbitals. And when I hybridize them, I am combining the S room and one bed from the P room to make this new room, this new sublevel, SP. There are two beds in it, and then I have two of these P orbitals that are unchanged. And again, the energy difference between these is close enough that the electrons will fill them separately. So again, we have 4 half-filled orbitals. This is why carbon always makes 4 bonds, because all of these hybridizations end up with 4 half-filled orbitals. Here we have hydrogen with a half-filled orbital. So we can get an overlap between the hydrogen and one of those hybrid orbitals. Well, what we've got here is we have another carbon atom. So there's another carbon atom, and we have another hydrogen atom. So we can get overlap between one carbon atom and the other carbon atom. And then this carbon atom is going to overlap with hydrogen. So we've got sigma bonds connecting all of those. So we have these sp orbitals on the carbon. One overlaps with the hydrogen, one overlaps with the other carbon. On this carbon, the one is overlapping with the other carbon and the other one goes to the hydrogen. I'm gonna dare to try to draw a picture. So that's carbon, and those purple things are their sp hybrid orbitals. There's hydrogen and there's hydrogen. So this is the sigma bond between an sp orbital on one carbon and an sp on the other. And then here I've got an sp with an s on the hydrogen, and here's an sp with an s on the hydrogen. What I have left are two unhybridized p orbitals on both of these. So there's one. And then this one is sticking in and out of the screen. That one's harder to visualize. Those can form pi bonds. So I can get a p orbital with a p orbital. So that's up here. That's going to be one of these bonds. And then I can get another one with the other two p orbitals. And that's the second pi bond, the third bond. Hopefully it looks better when it's actually being drawn than when you try to look at the whole thing afterwards. It's like, well, it kind of looks like a lipstick test page or something. Does that make any sense? Do you have any questions about that? It's like, yeah, I know it's a bit much to get your head around. Well, that's my ugly picture. Here's a pretty picture, right? Here's the carbon, one sp hybrid, the other sp hybrid. Each of those is half-filled. One overlaps with the hydrogen's half-filled orbital. This one overlaps with the other carbon's half-filled orbital. Then we've got a p orbital up and down and a p orbital back and forth. And those are going to overlap side to side, making pi bonds with the other carbon's p orbitals. I know, right? It's kind of cool and perplexing and just really weird at the same time. So we can name these bonds. This one in the middle here is a sigma because it's end to end. And it's between two carbon atoms, and it's an sp orbital on each. This bond over here is also a sigma bond. That's the hybrid orbital sp on the carbon overlapping with the hydrogen, which is an s orbital. And that would be the same description as for this bond over here. And then I have two pi bonds. So pi, and it's between a carbon p orbital and a different carbon p orbital. So that's one p orbital, right? Going side to side. And then the other one's sticking in and out. Those are the unhybridized orbitals. Any questions?
Do you typically label every bond in the picture, or just one of each kind?
Do we label every bond or just one of each kind? On the worksheet, we're just going to ask you to label each kind, regardless of how many there are. Here, they're specifying that both of these are the same. They're drawing an arrow or a line to this one. They're not drawing a line all the way over here to that one. Yeah, so generally just you'd label one of each kind. Because the sp orbitals are linear, the geometry of the molecule is linear. That's consistent with experiment and with Vesper theory. So we look at this Lewis structure, right? And we look at this carbon and we say, well, there's 2 electron groups. 2 electron groups, no lone pairs, linear, right? So this should be linear and that should be linear, and so the whole thing's going to be just in a straight line. So this is getting ahead of the slides a smidge. But I'm writing S, P, P, and P on my fingers. It only works out if I have that written on my left hand, which is tricky because I'm left-handed. So I'm trying to write with a Sharpie with the wrong hand. I wish I could do it the other way, but I just can't, and I just feel like such an idiot. Yeah, I did this yesterday, but it wears off too much so that you can't see it. Okay, so I'm going to get ahead of myself, but how do we predict what the hybridization is? We're going to look at the Lewis structure, arrow. We're going to look at the Lewis structure and see how many electron groups are there around that carbon. 2 groups. 2 fingers, S, P. Yeah. See, yeah. Let's go back and look at this one. So here's the Lewis structure. Come on, pointer. Here's the Lewis structure up here. This carbon, how many electron groups are around it? 4. 1, 2, 3, 4. sp3 is the hybridization. Okay. How about over here? How many electron groups? 3. 1, 2, 3. sp2. Like that? It's more fun on your fingers. Really what we're doing is we're looking at how many electron groups, and then we're starting with the s, and we're taking as many of the p orbitals as we need to make hybrid orbitals equal in number to the electron groups. Because all of the electron groups are going to have 1 hybrid orbital. That double bond, that second bond is made with unhybridized orbitals. Well, we learned that elements in the 3rd period and larger elements can do expanded octets, right? Because there are d orbitals available. Ooh, that's a little too fat. So there's s orbital, and there's p orbital, and there's d orbital. And this has 3 beds in it, and this one has 5 beds in it. So S, P, and D. This isn't present on the 2nd floor, on the 2nd level, but on the 3rd level and above, if I need more than 4 orbitals, I can expand into this empty room, right? It's there, and I can just knock down this wall, and I can knock down this wall and put up a new wall over here, and that's S, P, 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 and D. right? Whoops, not that. S, P, 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 D. Those are the rooms they used to be in, and so we would call that sp3d. Or we could go farther and take 2 of the d orbitals. So you would use this if you needed 5 electron groups, right? 1, 2, 3, 4, 5. Oops. So sp3d hybridization. We're taking the s sublevel and all 3 orbitals in the p sublevel and one of the orbitals from the d sublevel. And we're going to combine them. We're going to hybridize them. We're taking 5 orbitals and we're going to make 5 degenerate orbitals. Same shape, same energy, just spread out in space. How do 5 things spread out in space? What do 5 balloons make? Remember the name of that? Trigonal bipyramid, right? And they even look like balloons. But again, it's important to remember that each of these purple balloons is the big lobe of one orbital. And here, the second little nubby lobe would overlap with the other one. So we're not drawing those, but this is 5 lobes, 5 orbitals. 1, 2, 3, 4, 5. Those unhybridized d orbitals are just going to sit there. They were empty before, they're going to stay empty. So these will make a trigonal bipyramid. Here's an example. Here's the Lewis structure for arsenic pentafluoride. We've got the arsenic and we draw the Lewis structure just the regular way, and then we look at the arsenic and we ask ourselves, well, how many electron groups? 5. 1, 2, 3, 4, 5. Oh, you're fun. You're very fun. So sp3d, so that's 5, right? And so here I don't know why they made them gold instead of purple, but they did. So those are making a trigonal bipyramid in the middle. And then each of those is overlapping with a half-filled p orbital of the fluorine. So the fluorines are looking like this, S and P. We're going to assume they don't hybridize. So that's what the fluorine's going to look like. It has one half-filled p orbital. And so that half-filled p orbital is going to overlap with the arsenic's hybrid orbital. And it's going to do that with each of them, and so we end up with a trigonal bipyramid molecule. Any questions? It just matches up so nicely with Vesper theory. But it goes farther. Well, what if we need 6? I'm going to take the S and the 3 P's and the 2 D's. Now, in the hotel, could you remodel these rooms and take the S room and one of the P beds and then some of the D beds? No, you can't. Because the beds are bolted to the floor. I just made this up. The beds are bolted to the floor, and you can break down the walls and move the wall over, but you can't move the beds, right? So it's always S, and then however many of the P's, and then into the D's until you get the right number. So this will give us 6 hybrid orbitals called sp3d2, right? And then we have 3 unpaired. I know you want to see the other d orbital, right? 1, 2, 3, 4, 5, 6.
When did you draw the D's?
I drew the D's when I was talking about it. That was okay because it was left on my right hand, so that worked out okay.
You realize that now you're going to see all this here in test one.
That's fine. That is absolutely fine. And I've had people say, well, is it okay to write on my fingers for the exam? I'm like, yes. If you want to come in with SPPPDD written on your fingertips, I'm fine with that, okay? Absolutely. Most of us will get to the point where we can just imagine it, though, and we don't actually have to Because, you go around the rest of the day and people are like, what the? It's just quantum mechanics, and then they shut up. Just chemistry. You don't want to know. Yeah, occasionally I do see chemistry people and like at my house, and they're like, "Oh, you talked about valence bond theory today." Yep. So here's an example of sp3d2. So here we have sulfur hexafluoride. We've got 6 fluorines, so we need 6 electron groups. So that tells us what the hybridization is. We need to hybridize 6 orbitals. And those are going to make, I kind of skipped over this, those are going to make an octahedron. Right? The 6 balloons, that's the blue and red balloon thing in the hood. Right? 6 makes an octahedron. And so here again, we're using fluorine. And so the fluorine has 1 half-filled p orbital, and it's going to overlap with the sulfur. Now, when we were doing Lewis structures, I told you, especially when we were talking about formal charges, I told you, well, fluorine usually makes just 1 bond. That's why fluorine usually makes 1 bond. Its unhybridized orbitals have 1 half-filled orbital, and that's the one that's going to overlap. Now, can it do other things? Well, fluorine can't. But chlorine and bromine and iodine can, because they have d orbitals that they can expand into. Sulfur normally would just make 2 bonds, but when it expands into the d orbitals, then it can make more. Okay, so here's where it finally gets to how do we know? Well, we really should look at the degree of hybridization, the kind of hybridization, based on what's going to give the molecule with the lowest energy. That's too much work. Good enough for Chem 1A, we're going to assign a hybridization scheme from the electron geometry of the interior atoms. So we're looking from our Lewis structure and we're counting electron groups. However many electron groups, that's how many hybrid orbitals we need. It's not 100% accurate, but it's good enough. So that's what we're going to go with. So this is a table summarizing the different hybridization schemes and their shapes. These shapes are exactly the same shapes that we talked about in Vesper theory. Right? So there's not really anything new here. This is the same number of electron groups. Why it keeps popping that up. So, to write hybridization and bonding schemes, we're going to start with the Lewis structure for the molecule. We're going to use Vesper theory to predict the geometry. We're going to select hybridization based on the interior atoms. Again, we're looking at how many electron groups, and then we get our fingers out, we figure out how many, what the hybridization is. And then, I'm not going to make you do this for an exam or anything, in large part because I don't want to have to evaluate your drawings. But then you would sketch the molecule starting with the interior atoms and its orbitals, and then show how it overlaps with the terminal atoms. And it's good to try doing that at least a couple of times, just so you can kind of get a feel for, well, for one thing, how hard it is for me to draw these stupid things, but also just, so that you can more picture it in your head. Because that's the most important thing. Can you imagine how this is going together? Then you can write down the hybridization scheme. And then labeling the bonds using sigma and pi notation. And so most of these parts we're doing in the worksheet or the combination of the 2 worksheets, but I'm not going to make you sketch the molecule. So this is saying, write a hybridization and bonding scheme for xenon tetrafluoride. We have to start with the Lewis structure because we can't just assume that there are 4 electron groups because there's 4 bonds. So we'd start with xenon in the middle and put the fluorines around. And then we'd have to count up the number of electrons. Right, there's 4 times 7 is 28 plus 8, there's 36. 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I need to put 4 more electrons in here. Well, xenon's a big boy. Period 5. Expand the octet. So I'm going to put these 4 extra electrons as lone pairs on the xenon. Okay? So we have to start with the correct Lewis structure. And then we're going to look at the xenon and ask ourselves how many electron groups? 6. 6 electron groups. So what's the hybridization? 1, 2, 3, 4, 5, 6. sp3d2. Anybody want a Sharpie? Oh, yeah. So that tells us the hybridization, sp3d2. So when we look at how this is going to go together, I want to draw the orbital diagram for the hybridized orbitals of the fluorine, of the xenon, and then the unhybridized for the fluorine. I'm going to just start with the fluorine up here. And again, we're only doing valence electrons. So this is S, and this is P, and here we've got that 1 half-filled orbital. So for xenon, I'm going to do the atomic orbitals and the hybrid orbitals because that's what it asks you to do on the worksheet. So for xenon, we've got S and P. It happens to be 5S and 5P. You can write that or not. And then there's 8 valence electrons. And so this is typical of a noble gas, and it's all full up, right? And so you say, well, that's not going to do anything. Well, not like that, it's not. But then there's this empty D subshell over here. If you're going to use the D orbitals on the worksheet to show in the hybrids, then show them empty for the atomic orbitals too. Because that way, however many boxes we start with, we should end up with the same number of boxes. So when this hybridizes, I'm going to have 6 that are together. And that's sp3d2. And so that's using this 1, 2, 3, 4, 5, 6. Those, well, that's maybe a little too light, a little too subtle. You see that better? So those are the ones that are being hybridized. And then what's left? Well, there's 3 d orbitals that are just sitting there doing nothing. And they're just going to sit there and do nothing still. Xenon has 8 valence electrons, so I'm going to put the 8 valence electrons into my hybrid orbitals. 1, 2, 3, 4, 5, 6. And now we have a choice for number 7. And like for carbon, when we were doing sp2 hybridization, we put the 4th electron in the p orbital, and so I could completely understand you thinking that we should put those other 2 electrons over here. But let's look at the Lewis structure to help us decide whether that's right or not. Do you see this lone pair on the xenon? There's actually 2 lone pairs on the xenon. So if I put my remaining 2 electrons, if I pair those up in the hybrid orbitals, these are my lone pairs right there. Okay? And then I have 1, 2, 3, 4 half-filled orbitals. So Each fluorine is going to overlap with one of these half-filled orbitals. What would the bond description for that be? Is it pi or sigma? Sigma. And it's between the xenon and the fluorine. And the orbital on the xenon is this one. I didn't leave enough space. sp3d2. And on the fluorine, it's an F orbital. F is for fluorine, it's a p orbital. And so there's 4 of those bonds. They all have the same description. Now, if we were trying to draw a picture of this, these 6 hybrid orbitals, how would they arrange themselves? Like 6 balloons? Like an octahedron, right? So here's my xenon, and it's got 6. 1, 2, 3, 4, 5, 6. Use your imagination, it's 3-dimensional. And then the fluorine is using unhybridized p orbitals, and I'll maybe do one here. And so that's overlapping. And so this is going to occur at all of these. No, not all of them. 2 of them are lone pairs. I realized as I was saying it that was wrong. So I have 2 lone pairs. You can put the first one anywhere you want. The second one for this octahedral would go on the opposite side.
When you're writing out the sigma bond,
Mm-hmm.
So I get the xenon sp3d2. Is that like a minus or like just like a?
That's a dash. Yeah, it's a dash. You could think of it as the bond between the 2 things if you want. It's just a dash to separate them. And then it got lost in my parentheses there. That's better. Any other questions? Let's do another one. Write a hybridization and bonding scheme for HCN. Again, we have to start with the Lewis structure. And the point of this is not to teach Lewis structure, so I'm going to do that pretty quickly. There's the Lewis structure. There's one central atom, right? How many electron groups? 2, right? 2 electron groups. So what's the hybridization scheme? SP. So if I start with carbon's atomic orbitals, and I'm going to hybridize this, I'm going to put the S and one of the P's together. So that's SP. And then I've got these other 2 that are left over, and those are P orbitals. They didn't hybridize. And then the carbon has 4 valence electrons, and so I put them in there and I go 1, 2, and then I'm like, well, what do I do now? Do I pair them up, or do I put them in the p orbitals by themselves? Well, let's get a clue from our Lewis structure here. If I pair these up, then I'm going to have 2 lone pairs and nothing available to bond with. right? What I see up here is that I have a bond here, and one of these is going to be a sigma bond, and then I need 2 pi bonds, and those are going to have to come from p orbitals. So they're going to get spread out. And I point that out because I recognize it's confusing. Why did I spread them out on this one but not on the xenon? We're never going to have half-filled d orbitals, if that helps. The p's will tend to fill up half full. When we get to the d's, we're just borrowing beds from that next room. And then we've got hydrogen. So this is carbon. We've got hydrogen with its s orbital. And we have nitrogen. And nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. So when we're finding out the bonding scheme, what kind of bonds are being made, I have a hydrogen and a carbon attached to each other. That has to be a sigma bond. So it's going to be a hybrid orbital on the carbon and whatever hydrogen has. So hydrogen, that's not what I wanted to do. We're going to have a bond there. And then I need a sigma bond with the nitrogen. So that's going to be this hybrid orbital and one of those unhybridized p orbitals on the nitrogen. So I've got a sigma bond there and a sigma bond here. And then I've got unhybridized p orbitals on my carbon and unhybridized p orbitals on my nitrogen. And so they're going to overlap to make pi bonds. Okay? So if I describe these, it's a pi bond. How do I know it's a pi bond? Well, this is a triple bond. There has to be some pi bonds. There's always one sigma, and then the rest are pi bonds. And here I'm going p to p, p and pi. This pi, p pi, pumpkin pie. This is between the carbon using a p orbital and the nitrogen using p orbital. And it's the same for this other one. This bond, what kind of a bond is that? Sigma. And it's between carbon and nitrogen. And what orbital on carbon? sp. And on the nitrogen? The p orbital. Right? So I've got, this is my nitrogen. I've got a p orbital overlapping with on carbon and sp. And so that's what this is saying. sp on carbon overlapping with a p orbital on nitrogen. And then I have one other one over here, also sigma, and I'm going between carbon and hydrogen. And on the carbon it's sp, and on the hydrogen it's s. So on the worksheet, you're going to need to draw some electron diagrams for the central atom, the unhybridized, and for any of the terminal atoms unhybridized, and then the hybrid orbital diagram for the central atom. And then you're going to give the bond descriptions. You don't have to draw these lines like this. You can if you want to. And I'm not going to make you draw a picture, but I'll draw a picture for you. So here's the carbon. It's got an sp and an sp, and then that's one p orbital. Remember, the p orbitals have 2 lobes. The hybrid orbitals have 2 lobes, but we're only showing the big one. And so then we've got this one coming in and out. Hamburgers. We only draw the meaty part of the drumstick. And then for the nitrogen, nitrogen's over here. And I'm not going to draw the S because it makes things confusing. I'm just going to draw the half-filled one. So I've got 3 half-filled p orbitals. So there's 1, 2, 3. And then for the hydrogen just has an S. Oops. So I've got a pair of electrons there. This is a sigma bond. I have a pair of electrons here. This is also a sigma bond. My pi bond, I have a half-filled half-filled orbital here and a half-filled orbital there. Remember, they can switch their spins. And so this is going to overlap side to side. And that's one of these p to p pi orbitals. And then the other one is sort of behind and on top here. Any questions? Oh, there's one more. I thought that was the last one. Oh well. Let's just check. Okay, this is the last slide, and then we seriously will take a break. Carbon dioxide. We go through the process to draw the Lewis diagram, and we come up with that. How many electron groups on the central atom? 2 electron groups. So what's the hybridization? sp. So I'm going to draw the orbital diagram for carbon. Looks like that. And then when I hybridize it, I'm going to take this s orbital and one of the p orbitals over here to form the sp hybrid orbitals, and then I've got p orbitals sitting there. Carbon has 4 valence electrons, and so as I put them in, I'm going to put 1 each in these sp orbitals, and then do I go up to the p's or do I pair things up? I need to go up to the p orbitals. The energy difference there is not much, and I can tell I'm going to need these because I have a double bond here, which is going to require a pi bond, and a double bond here, which is going to require a pi bond, and it's these p orbitals that do the pi bonds. Then I have oxygen. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. And there's 2 of those. So between the carbon and the oxygen, I need to make a sigma bond. The sigma bond is always going to be the hybrid orbital. So I'm going to take the hybrid orbital of the carbon and overlap with one of the p orbitals on the oxygen. And then I guess we kind of need to put the other oxygen in here. And another one, p orbital on the oxygen with the sp on the carbon. So here I have carbon sp hybrids, right? And my oxygens, the half-filled orbitals, are p orbitals. So there's a sigma bond and a sigma bond. So this is the drawing of, I'm imagining the overlap of this with that, and this one with this one. And then I have a p orbital on this oxygen, a p orbital on that oxygen, and I have two p orbitals here. And so I'm going to get a pi bond for that one. And then over here, so if this is px and that's py, is this going to use the py to overlap with this carbon? This one's already being used. The carbon has a second p orbital, right? It's got the two p orbitals. So this oxygen is going to use the p orbital that's lined up with the remaining orbital on the carbon. The oxygen has two lone pairs. If I wanted to draw those, I'd have a p orbital with lone pairs, and I'd have an s orbital with lone pairs. And I could do the same thing over here. Let's label the bonds. So, whoops, not that one. Oh yeah, that one. And this one. What kind of bond? A sigma between carbon, which orbital on carbon? sp. And the other atom? Oxygen, p. Carbon, sp, overlapping with oxygen's p orbital. That's both of these sigma bonds. And then these other bonds, those are going to be pi bonds between carbon and oxygen. And what orbitals are used? P orbitals on both, right? Any questions?
So when you have lone pairs on a central atom, you normally stay in the hybridized orbitals and fill before expanding to the
Right. If I had a lone pair here, I would need to have a lone pair here in the hybrid orbitals. Yeah.
Does this same process work for molecules with more than one central atom?
Yes. Yeah. We can look at this hybridization scheme for all of the interior atoms. Yeah.
Shouldn't there be two lone pairs on the oxygen?
Yes, there should be two lone pairs on the oxygen. So here's an oxygen lone pair. And the other's in the s orbital. So I've got this s orbital and a p orbital. Any questions?